You care because multimodal AI stops being a collection of separate tricks and starts behaving like one coherent system that preserves meaning. Old models treated each input type as its own language game. Vision lived in pixels, speech lived in audio frames, and text lived in tokens. Translation between them worked, but it was brittle. The real scientific shift came when modern multimodal models learned a shared joint embedding, sometimes called a latent space. In that space, vision, speech, and text map into compatible coordinates. The mechanism is simple. The model trains with alignment signals so that related things land near each other, even if they started in different modalities. A train station map makes this clear. Every platform text gates, image platforms, audio docks connects to the same central transfer hall. Passengers do not keep switching cities. They switch lines inside one station. When you retrieve an image using a spoken description, you're not converting speech into text and hoping the meaning survives. You're moving through the shared hall. Watch this signal. If the model can answer what is happening by grounding features in an image, and it can answer the same what is happening from audio, then it has learned cross-modal correspondences, not separate pipelines. In practice, one of your concrete use cases is medical search. A clinician uploads a chest x-ray, speaks the concern, and the system returns studies that align in the same latent space. It compares, transfers, and grounds across modalities because everything is represented in one place. The last payoff from the silo-breaking story was that multimodal systems can talk to each other. The next mechanism is how that shared space becomes a foundation for reasoning, not just matching. If you rely on multimodal AI, your biggest risk isn't that it can't talk, it's that it can talk without truly seeing, like a detective who writes a conclusion before checking the evidence. So here's the shift. Grounding becomes necessary when the model must answer questions that depend on visual evidence, object identity, spatial relations, even the sequence of actions. Not sounds right. Not likely. It has to produce claims that can be anchored to what's actually in the image or video. When it does that, the system stops the old failure mode where text-only models stay fluent but ungrounded. Think about it like invisible markers on a scene. A grounded answer doesn't float. It points. It says, that object on the left is the one where this person is reaching before the handoff, and the claim has a visible anchor point. Without that requirement, the model can remain confident while hallucinating geometry or swapping entities because nothing forces consistency with the pixels. Now ask your first sharpening question. What happens to accuracy when the output must be verifiable against what the model sees? The second question is more brutal. How do you detect the difference between plausible and grounded during generation? And the third question locks the mechanism in place. If the model can't justify its statement with an evidence match, does it still sound right? Watch this signal. When a grounded, multimodal model answers what is happening from an image, then the same event description from another modality. It can be checked for agreement. Did it select the same entities and the same spatial relationships? That's the measurable consistency check. The System S statements must line up with visual evidence, not just with language patterns. And this is why the next mechanism matters. Because grounding is the doorway from matching to reasoning, so the model can start treating the world as constraints, not decoration. Your real edge with multimodal AI is that it can reason using evidence you didn't explicitly put into the words. Picture a control room where multiple sensor feeds converge into one dashboard. Camera streams, audio channels, telemetry, and charts that update in real time. You, the operator, make a call only when the dashboard supports it. In a text-only world, the operator never sees most of the signals, so the decision is built from language clues and prior expectations. It sounds coherent, but the mechanism is blind to the hidden drivers. Cross-modal reasoning changes that by letting one modality interpret another. If a model reads a chart from an image, it can use the visual trend as backing for a textual claim without you manually extracting features like slope, axes, or outliers. If it hears audio prosody, it can infer intent from how something is said. Not just what was said, then use that inferred intent to constrain the meaning of the transcript. The key is that information from one channel becomes the lens for another. So the conclusion updates when previously ignored signals flicker into relevance. Here, S the signal to watch. Suppose a dashboard shows a sudden spike, but the text report stays calm. A multimodal system can align the narrative with the chart. It can say, the spike at 14:05 explains the anomaly, because the visual evidence and the textual explanation are being linked during reasoning, not stitched after the fact. Now the question that matters for adoption isn't just, can it answer? Can it build the argument chain across modalities without turning the join into a loophole? Next, we'll look at how those cross-modal chains are trained and evaluated so they stay consistent under new conditions. When you deploy multimodal AI, the hard part is no longer getting an answer. It's proving the answer is reliable across lenses. Text-only evaluation often treats accuracy like a single scoreboard, correct or incorrect. Multimodal evaluation does something stricter. Imagine a multi-lens quality inspection machine at your factory. One lens reads the product label, another checks the surface, a third verifies the embedded code. It rejects the item whenever any lens disagrees, even if one lens sounds confident. Your system needs the same refusal mechanism. Measure agreement between modalities, not just performance within one channel. So the alignment shift starts with metrics you can actually audit. You score not only task accuracy, but multimodal consistency. Do the visual content and the textual claim cohere on the same entities, timestamps, or measurements? You score calibration under distribution shift. When the world changes lighting, camera angle, accents, background noise, does the Model S confidence drop in the right way? Or does it stay falsely certain? And you score robustness to adversarial or ambiguous inputs. If an attacker swaps the chart style, muddies the image, or blurs key audio cues, does the system still converge on the same joint interpretation? Or does it collapse into a confident hallucination? Watch the signal. A system reads a medical image and produces a confident diagnosis text. But the image-text consistency score flags a mismatch because the described lesion type doesn't match what's visible. That single disagreement becomes the detector, the bottleneck, the reason you catch the failure before it ships. In science terms, you're testing reliability as a coupled system: evidence agreement, uncertainty correctness, and joint resilience. Next, we'll translate this evaluation mindset into concrete training and test protocols so the alignment stays stable when the real world stops behaving like your benchmark. You're about to see multimodal AI stop describing the world and start operating on it, because understanding has to become a decision system. Picture this. You're standing a few feet from a robot arm. Its camera feed is live, and you can see a shared world sketch canvas. Beside it, boxes for objects, arrows for motion, a rough map of what's reachable. The robot doesn't just answer questions about the scene. It interprets a new frame, extracts the current state from the pixels, and then asks one brutal question: what actions are justified by what the sketch can actually support right now? Here's the mechanism shift that makes chat feel obsolete. In a pipeline, multimodal representations don't end in words. They feed directly into planning and control loops. Visual evidence updates the world model. The model chooses candidate actions. Then the system checks constraints against that same world sketch. No action gets executed unless the perception stack and the planner agree on the entities and their relationships. Watch this signal. The robot sees a wrench on the table, but the sketch flags uncertainty about its exact orientation because the image is slightly blurred. Instead of confidently just grabbing, the arm slows, reframes the camera, and rechecks the state estimate. The behavior is boring in the best way. Perception uncertainty turns into a control decision, not a post hoc explanation. Now connect that to product reality. If you build only chat, you get plausible narratives. If you build perception to action pipelines, you get bounded behavior. Pick only from actions the shared multimodal sketch can justify. That's how alignment changes from rhetoric to enforcement, from sounds right to measurably correct under motion. Next, the question becomes how you train and validate these pipelines so the world model stays coherent. When the environment shifts mid-task, because the moment you move from bench videos to real-time operations, that's where the bottlenecks reveal themselves. So here's the contrast you should keep in your head. At first, you treated multimodal AI like a convenience, an upgrade that reads and sees. But the real shift is system level. Multimodal AI becomes the interface between perception and reasoning, aligning images, audio, and text into one shared latent model that planning can trust. That's why product behavior changes. You can predict how it will act, not just what it will say. And you can evaluate deployments with clear criteria: latency, grounding, reliability, and multimodal consistency under real motion and messy inputs. If you're building or buying AI, stop asking, is it impressive? Start asking, is it bounded, testable, and coherent?